One of the most common ones that I generally will encounter in talking with a lot of different folks in a variety of industries is heat flow meters and guarded hot plates. These are your classic dual-sided plate design setup where the sample is placed in between, again, measuring the heat flow through the material. And there's some things to keep in mind here. Heat flow meters, guarded hot plates, sometimes referenced by the ASTM standard, so ASTM C518, C177. By and large, in the insulation industry, they are viewed as a golden standard, especially when it comes to product certification testing. It is something that is just very well ingrained in that industry. Really good for lower conductivity. There are certain heat flow meter style setups that push this upper range a little bit, but generally, if you kind of look across the board, most commonly referenced for samples below 1 watt per meter Kelvin. Really good at measuring across the full thickness of a material. This is one of the inherent benefits of a steady state and specifically heat flow meter style setup is it's capable of testing through the full thickness. You can also look at testing multi-layered materials. They've got some nice advantages going for them here. But there are certain things to flag. Again, I really mentioned that these are designed most commonly for like insulative testing. So things like your batted or foamed insulation, foam boards, whatever that may be. And again, commonly referenced on technical data sheets for this for insulation. So you can see C518. Now they're putting this in terms of R value, but R value is just the thickness of the material over conductivity. But again, using the C518 method to get at that type of data. Now, that being said, there are certain considerations to be aware of here. One of them is that steady state in general will have a much longer test time. So this is true across the board. They're typically hours, some systems, and depending on the conditions, can even be days. One of the reasons behind this is, again, you're waiting for that steady state condition to be met. So it does inherently require a longer duration. And if you are looking to conform strictly to the C518 standard, there are certain requirements in there that must be met in terms of, measurement consistency and stability, modified testing procedures are certainly employed in many cases. But if one of the main advantages of using a steady state or heat flow meter, for example, is to, conform to the C518 standard, well, again, you're going to want to make sure you're checking all those boxes there. So longer in duration. One of the other big ones, especially for groups working in an R&D environment, is that they do carry some stricter sample geometries in the sense that your dual-sided plate design, typical sizes, 30 by 30 centimeters, or about a foot by a foot. The thickness ranging, typically in the centimeter range. But, there are many groups that are producing samples that are just very small, especially, again, early R&D stages where you're not able to produce at the volume or the size that is typically used for these more traditional methods. There can be certain challenges there on that front. As I was saying, not really designed for high K. It's essentially when you're getting those very high levels of heat flux, you're not able to maintain that stable temperature gradient. This is where you'll start to get some bias introduced, and just again, simply where the performance range isn't really designed for. And as I said, one of the benefits, of course, is measuring through the full thickness. And while that in one context is quite advantageous, what you lose out in a device that measures across like a larger area, kind of averages everything out, is if you're experiencing consistency issues. Again, maybe that's across the surface, from side to side. Those types of issues aren't as really detectable with these more traditional approaches. We'll talk about how we can address those with some transient options here, but